In the last section of Chapter 11, we're going to talk about colligative properties of solutions. Now, colligative properties are solution properties that depend on the concentration of solute particles, but not the identity of the particle. So it doesn't matter if we're talking about calcium chloride, sodium chloride, methanol, whatever it is. Colligative properties only depend on how many particles are in solution, or how many ions, for example. And we'll talk about that a little bit later on in this chapter. But what are the consequences of colligative properties, or dissolving a solute in a solvent, is vapor pressure lowering, and that can change both the boiling point and the freezing point of a solution. So if we look at this phase diagram, and if we look at the 1 atmosphere line, notice that the original boiling point was right here, okay, at this temperature. Whereas if we add a solute to the solution, the new boiling point ends up being higher. Okay, so we're down here. And that difference in boiling point is going to be shown later as this delta TB. So when we talk about colligative properties, we need to define a new concentration unit, and that is called molality. So molality is the moles of the solute per kilogram of solvent. So similar to molarity, remember molarity is moles of solute per liter of solution, but in this case we have kilograms of solvent as the denominator. So we're using molality because it is a temperature independent concentration. So to calculate molality, I have a little bit of a flow chart here for you to follow. So if you start off with the mass of the solute and the mass of the solvent, then the only thing you have to do is to convert the mass of the solute into the moles of the solute. Okay, and to do that, you would use the molar mass. Okay, you could also start with the mass of the solution, and if you start with the mass of solution, then you're going to have to turn the mass of solution into the mass of the solute, and so then you have to know how many moles of solute is in there, how many moles of solvent there is, and then convert both of those into masses and do a subtraction. If you start off with the volume of the solution, then you have to multiply by the density in order to get the mass of the solution, and then from there get the mass of the solvent. And again, this ratio here is going to be the molality, right? The moles of the solute divided by the mass of the solvent. And that's going to get you the molality. So here's a quick example to determine the molality of a solution. Now this is the simplest example possible because I'm giving you both the moles and the mass of the solvent. So this is simply just dividing the moles by the kilograms. So we're going to have the molality equals 0.875 moles of glucose divided by 1.5 kilograms of water. And that's going to equal 0.58 molal. Okay, so that's a very simple calculation. We'll get into some more difficult ones a little bit later. So here's just a summary of concentration expressions and what advantages they have and the typical uses, and also the units of each one of them. So molarity, molality, and mole fraction we learned about in this chapter. And mass percent is something that you may have learned in a previous class, but we're not going to use that one too much in this class. So the first three are the ones that we're going to be using most in this class. So one of the colligative properties that we're going to talk about is boiling point elevation and freezing point depression. So basically what that means is if a solute is added to a solvent, so say sodium chloride is added to water, the boiling point of that water is actually going to increase, So instead of being 100 degrees Celsius, it would be greater than 100 degrees Celsius. And the difference in that temperature, or the amount that the temperature is going to be elevated, will depend on how much of the solute, how much of the sodium chloride is added to the water. And if we look at freezing point depression, that means that if we add sodium chloride to water, the freezing point is going to decrease. So instead of water freezing at 0 degrees Celsius, it would freeze at less than 0 degrees Celsius. And again, the amount below 0 degrees Celsius that it freezes at is going to depend on how much sodium chloride is in the water. Okay, so this flow chart on the left just shows how you would go through a calculation, and we also have the equation here. So this is the boiling point elevation equation, and down below, looking very similar, is the freezing point depression equation. Okay, so this delta TB is the change in the boiling point. Right? So if the original boiling point of water is 100 degrees Celsius, and the new boiling point after adding some sodium chloride was 102 degrees Celsius, the change in the boiling point, or the delta TB, would be 2 degrees Celsius. M in both cases is molality, and Kb and Kf are constants that depend on the identity of the solvent. So water is going to have a different Kb than other solvents like hexane or whatever it might be. Okay, so let's go through another practice. So we have a question that says cinnamon owes its flavor and odor to cinnamaldehyde, C9H8O. Determine the boiling point elevation of a solution of 100 milligrams of cinnamaldehyde dissolved in 1 gram of carbon tetrachloride, and it's giving us the Kb, or the boiling point elevation constant. Okay, so the first thing that we should do in this case is to figure out what the molar mass of cinnamaldehyde is, because we're going to need to find out the moles of cinnamaldehyde, right? So cinnamaldehyde in this case is the solute, right? Because we can see that the cinnamaldehyde has been dissolved in 1 gram of carbon tetrachloride. So we need to know the moles of cinnamaldehyde, and in order to do that from a mass, which is 100 milligrams, we're going to need to know the molar mass of cinnamaldehyde. Okay, so molar mass of cinnamaldehyde. Okay, so we have 9 carbons, 8 hydrogens, and 1 oxygen. Okay, so carbon, we have 9 of them, and they have a molar mass of 12 grams per mole. Hydrogen, there's 8 of them, and we have the molar mass of 1 gram per mole, and oxygen is 1 of them, and they have a molar mass of 16 grams per mole. So if we figure that out, do the multiplication, we end up with a molar mass of cinnamaldehyde equaling 132 grams per mole. Okay, so now we need to figure out the moles of cinnamaldehyde. So moles of cinnamaldehyde. Okay, so we're going to start off with the mass. So we have 100 milligrams of cinnamaldehyde. And we need to turn milligrams into grams because our molar mass is in grams. So times 1,000 milligrams per 1 gram. So that cancels out the milligrams. And then we have the molar mass of cinnamaldehyde to cancel out the grams. So 132 grams cinnamaldehyde per 1 mole. And that cancels out grams. And if we calculate that, we end up with 7.56 times 10 to the minus 4 moles. Now we need to figure out the mass of our solvent, of the carbon tetrachloride, but it has to be in terms of kilograms. Okay, so it's given to us in grams. So we got to turn that into kilograms. So mass carbon tetrachloride equals, and if we go back up, we can see that it is 1 gram of carbon tetrachloride. So 1.00 grams of carbon tetrachloride times 1,000 grams per 1 kilogram. So that's going to give us 0.001 kilograms of carbon tetrachloride. Okay, so now we have moles of cinnamaldehyde and the mass of the solvent. We can figure out the molality of the cinnamaldehyde. So molality is going to equal 7.56 times 10 to the minus 4 moles of cinnamaldehyde per 0.001 kilograms of carbon tetrachloride, and that's going to be 0.756 molal. Okay, so now we have all the information we need to figure out the boiling point elevation. So delta TB equals KB times molality, and our KB is 2.34 degrees Celsius per molal. Our molality is 0.756. So delta TB ends up being 1.77 degrees Celsius. So whatever the original boiling point of carbon tetrachloride is as a pure liquid, adding a small amount of cinnamaldehyde is increasing that boiling point by 1.77 degrees Celsius. Okay, so now what happens if we have an ionic solute? So for example, sodium chloride. So cinnamaldehyde is not ionic. So when you dissolve cinnamaldehyde, it's just an organic compound. It doesn't split up into any ions. The molecule itself just dissolves as a whole molecule. Whereas if you put in something like sodium chloride into water, it's going to break up into sodium ions and chloride ions. So remember, the colligative properties depend on the number of particles in the solution. So by dissolving sodium chloride is going to result in 2 particles, right? Sodium plus and a chloride minus. So we have to correct for this. Okay, so when we're dissolving an electrolyte, something that does ionize in solution, we have to correct for the number of particles in solution. And this is called, or the correction factor is called the Van't Hoff factor. Okay, so the Van't Hoff factor is basically the number of ions in a formula unit. So for example, sodium chloride breaking up into sodium plus and chloride minus, the Van't Hoff factor, or I in this case, is going to be 2 because there are 2 particles. For calcium chloride, CaCl2, that would break up into 1 calcium, 2 chlorides, which would be 3 particles, so I in that case would be 3. So the equation for boiling point elevation and freezing point depression are pretty much the same as what we just saw. The only difference is that we have an I in front of the constants. So that I is going to be the Van't Hoff factor. Now, it's not always the case that the Van't Hoff factor is going to be equal to the number of ions in solution. So sodium chloride is not always going to have a Van't Hoff factor of 2. Calcium chloride is not always going to have a Van't Hoff factor of 3. It will at low concentrations, but at high concentrations, the ions act less like individual particles, and sometimes they act more like they're still stuck together. So I'm just going to zoom up on this, the bottom right-hand corner. So on the left-hand side, this is a low concentration of sodium chloride, right? 0.01 molal. We're looking at molality again. So you can see in this case that the chloride ions in green and the sodium ions in orange are separate. They're acting as individual particles. But as the concentration gets high, what happens is this ion pairing, right, which is shown here circled in red. So some of the ions are acting as individual ions, others are acting as paired ions. So the Van't Hoff factor, instead of being 2 in this case, would be a little bit less than 2, maybe 1.7, 1.8, or something like that. Okay, so the theoretical Van 't Hoff factor would be the one that you would expect just based on how an ion would break up. The actual Van 't Hoff factor, or the observed Van 't Hoff factor, would be what would occur in solution. So if we had a higher concentration of solution, this number would always be less than the theoretical Van 't Hoff factor. So the next slide I have some examples of a theoretical versus a measured Van 't Hoff factor. So we have sodium phosphate first. So sodium, there's 3 sodiums, so it would be 3 sodium plus and 1 PO4 minus. Remember, phosphate, PO4 minus, is a complex anion, so it doesn't break up into phosphorus and oxygen. Same with the next one, potassium sulfate. 2 potassiums, 1 sulfate, SO4, 2 minus, is a complex ion. Okay, so notice that the theoretical Van 't Hoff factor is equal to the number of ions that each of these breaks up into, but the measured Van 't Hoff factor at a concentration of 0.1 molal is always less. Okay, it's always going to be a little bit less. And in the case of a homework question, quiz question, or exam question, I could ask you to use the theoretical or the measured Van 't Hoff factor. If I was to ask you to use a measured Van 't Hoff factor, I would have to give that to you. But if I was just asking you to use the theoretical Van 't Hoff factor, then you should be able to figure that out, what the number is, based on how each of these ionic solids break up. Okay, so just to go over how those would break up, right? So sodium phosphate would break up into 4 ions. Potassium sulfate would break up into 3. Calcium chloride would break up into 3. Magnesium sulfate would break up into 2. 1 magnesium, 1 sulfate. Sodium chloride into 2. 1 sodium, 1 chloride. And ethanol, it's not ionic, so its theoretical Van 't Hoff factor is going to be the same as the measured Van 't Hoff factor. Okay, so only ionic solids, only things that break up into ions, will have a measured Van 't Hoff factor that is less than its theoretical. If the Van 't Hoff factor is 1, it's going to be 1 both theoretically, and that's also going to be the measured Van 't Hoff factor. Okay, so let's just go through a little bit of practice. Maybe you want to pause the video, see if you can do these yourself. So what is the theoretical Van 't Hoff factor for KBr? KBr will break up into K plus Br minus. So that's going to be a Van 't Hoff factor of 2. CH3OH, that's not ionic, so that just goes to CH3OH still, doesn't do anything. So that would have a theoretical Van 't Hoff factor of 1. And Na2SO4, we go to 2 Na pluses plus an SO4 2 minus, which would end up being 3 as a theoretical Van 't Hoff factor. Okay, so one more practice for Van 't Hoff factor here. This question is asking us whether calcium chloride could be used to melt ice at minus 20 degrees Celsius, and it's given us some information to help us with that. Okay, so the first thing that we should do in this question is to realize that we're going to need molality, and to get molality, we need moles of something. So what do we need the moles of? We're going to need the moles of our solute, and the solute in this case is calcium chloride. The solvent is water. So we're going to need moles of calcium chloride per kilogram of water. We're not given the moles of calcium chloride. We're given a mass, or at least what it would be, how much could possibly dissolve in 100 grams of water. So we're just going to assume that we're going to have 70 grams of calcium chloride, and we're going to put that into 100 grams of water. So let's figure out the moles of calcium chloride given this information. The first thing we're going to need to do is figure out what the molar mass of calcium chloride is. Okay, so molar mass, calcium chloride. Okay, if you want to look this up on the periodic table, you can, but it ends up being 110.98 grams per mole. Right, so now we need to figure out the moles of calcium chloride that we have in that 100 grams of water. So moles of calcium chloride is going to equal what we started with. So 70.0 grams of calcium chloride. And then we're going to divide that by the molar mass. And that's going to give us 0.6307 moles. Okay, so that's how many moles of solute. Now we need to figure out molality. So remember, molality being the moles of solute over the kilograms of solution, the kilograms of solvent. We have 100 grams of water, which is the same as 0.1 kilograms. So we can easily figure out the molality of calcium chloride being 0.6307 moles per 0.1 kilograms, and that's going to give us 6.307 molal. Okay, so what are we asked for? We're asked for a freezing point depression in this case. We're given a Kf of 1.86 degrees Celsius per molal, and since we have an ionic solid, calcium chloride, we have to consider the Van 't Hoff factor, and we're given the Van 't Hoff factor right here as 2.5. So if we want to write this out, we have our freezing point depression is going to equal the Van 't Hoff factor times the constant times molality. So that's going to equal 2.5 times 1.86 degrees Celsius per molal times 6.307 molal, and that's going to give us a freezing point depression of 29.3 degrees Celsius. Okay, so remember that's just the freezing point depression. We're asked whether or not this amount of calcium chloride could be used to melt ice at minus 20 degrees Celsius. So the original freezing point of water is 0. So the new freezing point of water is going to be 0 minus 29.3. So new freezing point equals 0 degrees Celsius minus 29.3 equals, of course, minus 29.3 degrees Celsius. So that's telling us that water with a saturated amount of calcium chloride in it, dissolved in it, will now freeze at minus 29.3 degrees Celsius rather than 0 degrees Celsius. So if the temperature outside is only minus 20, it's not yet going to be frozen because it freezes at minus 29.3. Okay, so the last colligative property I want to talk about is osmosis and osmotic pressure. Okay, so osmosis is this movement of solvent through a semi-permeable membrane. Semi-permeable meaning that only certain solvents or solutes can pass through that membrane. Okay, some things will stay on either side of that membrane. They're not allowed to pass through. And the solvent going through a semi-permeable membrane is always going to move from a region of low solute concentration to a region of higher solute concentration. Okay, and we'll go through a couple examples in a minute here. So osmotic pressure is the pressure required to stop the flow of solvent through that membrane due to osmosis. Okay, and then this is the equation for osmotic pressure. Okay, pi here being osmotic pressure. I is the Van 't Hoff factor. M is molarity in this case, so this is not the same molality that we've used so far. In this case, we use molarity. And then R, universal gas constant, 0.08306 liter atmospheres per mole Kelvin for R, and then temperature being, or T being the temperature in Kelvin. So this is what it would look like if you had two different solutions on either side of a semi-permeable membrane. Okay, so semi-permeable membrane being this guy here in the middle. And one side of this container, it's an open container on each side, so we have sodium chloride at 0.1 molar concentration on the right-hand side, seawater at a higher concentration on the left-hand side. And the membrane is only permeable to water. So none of the salt from the seawater, none of the sodium chloride can get across that membrane. So the solvent is going to move from a region of low solute concentration to a region of high solute concentration. So that means that the solvent must move from right to left. Okay, so water is going to be moving from the right-hand side to the left-hand side. And what you can see happens is that the volume of the left-hand side ends up increasing because water is moving across that semi-permeable membrane. And the difference between where that water ends up on the right-hand side and where it ends up on the left-hand side is the osmotic pressure. So how much pressure is going to be required to stop that flow from happening is going to be determined by that distance. If there's more pressure, that more of that water is going to be flowing from right to left, which will create more of a difference in the levels of water. Okay, a couple examples of what osmosis would look like under medical conditions. So this is a picture of a blood cell. Under normal conditions, the blood cell looks kind of like a donut. Okay, that's when the amount of solute or salt is the same both inside and outside of the cell. This is called isotonic. If we have a hypertonic situation, that's when water is flowing from inside the cell to the outside of the cell. Okay, so that's when we have more salt outside of the cell than we do inside of the cell, right? So the low solute concentration would be inside the blood cell, higher solute concentration outside the blood cell. And in this case, the blood cell would kind of shrivel up because it's losing water. If we have a hypotonic situation, that's when the solute concentration inside the cell is higher. So in that case, what would happen is the water from outside the cell would be rushing inside the cell, and then that would kind of blow it up like a balloon. And if there is too much of a difference in the concentration, then that cell would just end up bursting. You may have heard of something called reverse osmosis, and that is just the reverse process of osmosis. So instead of the solvent going from a region of low solute concentration to a region of high solute concentration, it would be just the opposite. But since the process of osmosis is a spontaneous process, which means that you don't have to do anything except put those solutions on either side of a membrane. In order to make reverse osmosis happen, you have to add pressure to the side of the container that is increasing in volume. So you basically have to push the solvent through that semi-permeable membrane using some energy. And one application of this is desalinating water, so taking the salt out of water. Right? So we have a high concentration of salt water. We want to remove the salt, so in order to do that, we'd have to push that water through a semi-permeable membrane to remove the salt and in the end get some pure water on the other side of that membrane. Okay, so let's just go through an example of osmosis sort of pictorially. Okay, so we're going to have a container divided by a semi-permeable membrane. It's only permeable to water. And on one side we have sodium chloride, and then the other side we have a higher concentration of sodium chloride. So the question is asking what flows where. So if we were to draw a container just like we had in the previous slides with a semi-permeable membrane in the middle, and what do we have on the left side is 0.1 molar NaCl, and then 0.2 molar NaCl on the other side. The question is what flows where? Right, so remember, the only thing that is flowing is in osmosis, unless the question says otherwise, is the solvent. So the solvent in this case being water. And remember, it flows from a region of low solute concentration to a region of high solute concentration. So the water should flow from left to right. And that's the only thing that's going to be flowing. The sodium chloride is going to stay on either side. And basically what's going to happen is the water is going to continue flowing until the concentrations of sodium chloride are the same on each side. Okay, so once they're the same, then there's no pressure for that water to move. There's no concentration gradient, so the water is going to just stop moving once those concentrations are the same. Okay, so another example, if we have a container divided by a membrane again, it's permeable only to water. So let's draw a small one over here. Filled with an equal volume of a salt solution. All right, so I have equal volume of a salt solution. If the water flows from left to right, so if the water is going this way, which of the following statements is true? So osmosis means, again, that the water is flowing from low solute concentration to high solute concentration. So let's see, A, the solution on the right is more concentrated. That would be true, because if that was true, then we have a low on the left, low solute on the left, high solute on the right. So A is true. The volume of liquid on each side will be equal at equilibrium. Well, that won't be true because the water is flowing somewhere, right? It starts off initially at the same height, and then the water's flowing left to right, so the volume of the right-hand side is going to increase over time, so that B is not right. Reverse osmosis is occurring. Well, there's no indication that any pressure is being added, so C is not right. The volume of the solution on the left will increase. Well, if water's moving from left to right, then the volume of the right is going to increase, so D is wrong. And the solution on the right will become more concentrated over time. And if we're moving from low solute to high solute, we're diluting the solution on the right, so the solution on the right should end up getting less concentrated, so E is also not right. So the only thing that's true in this case is A. Okay, so one of the applications of colligative properties is to determine molar masses of solutes. Okay, so the most common application of this is through osmotic pressure. So using the osmotic pressure equation, the first step would be to solve for molarity. Okay, so we're just rearranging the equation to solve for molarity. Once we have molarity, we know that molarity is moles per liter. Okay, so if we have moles per liter, in the question we're going to have to given a volume. So we can rearrange this equation here to solve for moles. So this is going to be our moles of the solute. Is going to be the molarity of the solution multiplied by the volume of that solution. Okay, and in the question you'd also have to be given a mass of solute that was added to the solution. So if we end up here with moles, right, so we have moles, and molar mass is grams per mole. If we have grams in the question and we solved for moles, then just solving that equation is going to give us the molar mass. Now typically this is only used for non-electrolytes, so for solutes that don't break up in solution, and the reason for that is because we wouldn't necessarily know what that Van't Hoff factor is, if it's close to the theoretical Van't Hoff factor or not, so that would affect our molar mass. Osmotic pressure is the most common application, but it can also be done using freezing point depression and boiling point elevation. Okay, so let's just go through one practice question here. So we're given the freezing point of a solution prepared by dissolving 150 milligrams of caffeine in 10 grams of camphor is 3.07 degrees Celsius lower than that of pure camphor. We're given the freezing point depression constant, Kf, and we're asked to find the molar mass of caffeine. So since this is a freezing point depression calculation, we're going to be using this equation. Okay, so we're given delta TF as 3.07. Well, we're not going to actually need I because caffeine is a non-ionic solute, so we actually don't need I. We're given Kf, so we have to solve for molality. So M is going to equal delta TF over Kf, which is going to equal 3.07 degrees Celsius over 39.7 degrees Celsius per molal, and that's going to give us 0.0733 molal. Okay, so that's our molality. So molality, if we write that out in terms of its units, is going to be moles of caffeine per kilogram of camphor. So to figure out the moles of caffeine, we have to get rid of the kilograms of camphor. So if we multiply that by the 10 grams, which is 0.01 kilograms, then we end up with 7.73 times 10 to the minus 4 moles of caffeine. So now we have moles of caffeine. That's 1/2 of the molar mass equation, right? Grams per mole. We're given how many grams of caffeine that were used, so that's 150 milligrams. So now the molar mass of caffeine is going to equal the grams of caffeine. 150 milligrams is the same as 0.150 grams over the moles, which is 7.73 times 10 to the minus 4 moles. And we end up with 194 grams per mole for the molar mass of caffeine. So that's it for this chapter and this section. If you have any questions, feel free to send me an email, and we will start the next chapter, which is kinetics. And I'll warn you right now that there is quite a bit of math that is coming up, especially in that chapter, but pretty much in every chapter from now until the end of the term.